Good morning, all students. Welcome to the class. I'm sure now you have started practicing your binary trees, and I'm sure you have also explored binary search tree, but you have still time to explore and implement binary search tree. But I'm expecting all of you have done binary tree by now. And now you have to recall the concept of a full binary tree followed by concept of a complete binary tree, which we discussed in the class before previous class. So in the second last class, we have discussed the concept of a full binary tree and complete binary tree. And we said that this concept will be quite useful to discuss heap sort, and that is where we are targeting to do today. So just to recall, first of all, let's recall what was a full binary tree. So if I represent a binary tree up to a particular level, then if all elements have both children, effectively it's a full binary tree. So out of full binary tree, if I keep on removing certain elements or children right backwards from the rightmost position, then it will become a complete binary tree. Why do we discuss all this was that this has a specific advantage, and once it is a complete binary tree, it can be numbered, or its nodes can be numbered in a way that we will be able to use it in a more smarter manner. So we will be able to have the advantage of this in a way that the left child or all that the tree properties will be possible to be used. Tree properties effectively could be useful via array itself. What do I mean? I mean a complete binary tree effectively can be stored as an array, and then we will be able to utilize any children, left or right child of any node will be possible. Left, right child's index, left, or I'll say left oblique right child index also will be possible to be found directly. And hence, in the array, it can be used. So no need to explicitly store it. And once it is an array, then over array, if I want to implement some sorting, etc., so that will become possible. How all this becomes possible? Let's have a look. Let's say if I assume that I have some data, for the simplicity, I'm taking the data which is used in the Horowitz-Sahni book itself. And out of that, whatever data they have used, I'm trying to draw the same thing here so that once you read from the book, you are able to correlate directly. So the book has assumed the data to be something like this. Let's say I have some binary tree. This is a complete binary tree with this data. And obviously this is root, and all other children, left, right children are existing. So I say, as it is a complete binary tree, of course, other nodes can be there. Then my nodes can be numbered starting from root and level order traversal direction wise numbered. Root becoming 1. Then the way we have a level order traversal sequence, they will be numbered in this way. 4, 5, 6, 7, 8, 9, and 10. And why I am numbering? I say, now this equivalently stored as array at respective indexes. So I can say the whole binary tree with all its properties at a 0 index, I will store nothing. But from 1 index onward, I will store the corresponding value. At index 1, 26. Node number 2 is 5. So I will have 5 here at index 2. Then I will have 70 level order traversal. 26, 5, 17, 116, 11, 161, 11, 59, 40, 15, 48, and 90. And if you see these numbers, the indexes are 1 to 10. So total 10 elements are there, n equal to 10. I say effectively the whole complete binary tree, which was of 10 nodes, could be stored in this form. But the advantage is that if I have any node number I can guaranteedly tell that its left child is at index 2 star I. Right child is always guaranteedly to be at 2 star I plus 1. And parent is always at I by 2. The numbering has this advantage. Of course, if node exists, if the corresponding node exists. For example, if left child exists, then correspondingly left will be at a 2i. If node parent exists, it will be at I by 2, etc. You can verify that. Node number 1, its left child is node number 2, 2i. Node number 3 is its right child, 2i plus 1. For node number 2, its left child is guaranteedly at index 4, right child at guaranteed index 4 plus 1, 5. For 3, 6 and 7. For 4, 8 and 9. For 5, 10. And if there was a right child, it will be at 11, but 5 has only left child at 10. Parent. 4's parent at index 2. 5's parent, 5 by 2, floor of that is again index 2. So I can now say if any node is at index I, then correspondingly your left child index is known, right child index is known, and parent child index is known. The advantage of this being from array itself, I can directly use left or right child or parent. So I need not to store it as a binary search tree or as a CBT. I can store it as an array, and this I will be able to use and access. For example, I say I am at node number 4 and say I want to go to node number 4's or value 1's left child. It will be guaranteedly at 8. This is left child. Its right child guaranteedly at index 9, 4 plus into 2 plus 1. Its parent will be guaranteedly at 2i by 2. And you can verify for node number 1, its left child is 15, that is this left child. Right child is 48, that is this right child. And parent is 5, you can see 5. So this property becomes useful, and what advantage in this case is that I will be able to use tree properties over array. So now, knowing this concept, I will recall and go further to explain how heap sort will work. So I will say I will have an array of n elements. Once I have an array of n elements, it will be visual. It is stored into as an array. You will visualize this or logically think it as a complete binary tree. Now, once you visualize it as a complete binary tree, I will say adjust, or that is another word called as a heapify your CBT as a max heap. So what is max heap? I will define, but now I am going to use another new structure or a data structure, which I call as a max heap. And once max heap is there, effectively it is an array. As an array. And I'll say either effectively or you say it is actually stored as an array. So using max heap property, using max heap's root, heap sort will be implemented. And max heap root effectively means it is always at index 1. So over the array, using index 1 for certain properties and slowly progressing or iterating that, I will be able to apply the heap sort. Hence, that's why we are talking of heap sort now, because it needed the concept of a binary tree and actually done over array, but concepts of a binary tree used, concept of left-right child used, and then it is used. But what is max heap? So the primary concept is max heap. I say in max heap, the property is that max heap is the CBT or whatever you are saying. It could be not a CBT, but it max heap effectively means the roots node or roots value is always greater than equal to its children, both children. So roots value must be greater than or equal to both children, and this has to be applicable, true, or it has to be applied on all nodes. So this effectively will be the main property to call it as a heap. So a heap effectively means root follows value behavior compared to its children. Max heap means root will have values greater than its children. Min heap will mean root will have values less than its children, less than or equal to. Not only that, it is applicable on all nodes. So effectively, if I say that I have here, let's say 75, that will mean this 75 has to be something greater than the left child and right child. Left and right will have any order. There is no guarantee that left will be smaller or left will be greater. But 75, this value is there. Similarly, 60 at all has to be greater than its left and right children. It could be even 56. There is no rule that others will differ. 55 has to be greater than any other value, let's say 30 and let's say 52. So this is effectively a max heap. All nodes are satisfying. 60 is greater than both children. 55 is greater than both children. 75 is greater than both children. Effectively meaning roots value will be the highest. So if roots value is highest, that becomes a basis of sorting. Main step of the sorting will become via this. So once I have a max heap, then my root is highest. So what I will do is this value, I will take it at the last of the array, or take it at the last of the array. How to take? Effectively with the last element, I can say I will swap it. So last element will be swapped and take it last element. And after that, I will say, now reduce your size of the array. Consider the length or the array list to be 1 lesser. Reduce the size by 1. Again, you have to then, now after this will be again heapified or adjusted to make it max heap. Once it is made max heap, again the root has the highest value. Again, I will do the same process. Now root has the highest value. I will take it at the last position of the current sized array. Size equal to n. So size reduced, n equal to n minus 1 has been done. So at the second last position, the second highest will reach. Again, reduce the size. So every time, just keep on extracting the highest and bring the highest to the last of the array. And then again, you have to make things as max heap and keep on processing. So this is overall heap sort. Overall concept I have given, but coding we will do systematically, understanding we will do systematically. So this is an overview given. Detailed clarity will come now once we talk further in detailed steps. So overview effectively, I mean, I have taken n elements array considering it as a CBT. Over CBT, I have converted that or adjusted that to become a max heap. From max heap, keep on extracting the highest element, extract your root and replace and reduce the size and consider shortened list. And keep on repeating every time you keep on extracting the root, which is the highest, and accordingly this process repeat. Knowing this, now let's try to go into further micro details. So I say, now I know what is the corresponding complete binary tree versus maxi. So if I say earlier I had this as my initial data where I had 626, 577, 1, 61, 11, 59, 15, 48, and 90. This data I had. This was my initial data. I say this has to be heapified, or in Horowitz and Sahni book, the operation name is called as adjust. In Corman, the algorithms book, which you will study in detail in next semester, this operation is called as a heapify, max heapify. So one and the same thing, both are same. And you can use any function name or any variable name. So we will say adjust oblique heapify word to be used to convert it to a maxi. Convert it will mean a particular node number. So how this function will work, it will say for a particular node. So I'll say effectively what I have to do. I say my doing process will be, I will start for those nodes which might not be satisfying the heapify max heap property. Which one is the first node? Leaves obviously satisfy. They are already heapified. They are maxi. Each heap, each leaf is already maxi because 19, it is greater than its children at its own level. So if I say leaf is considered as root, if you consider this as a tree and having a root, this is guaranteedly maxi. 19 is itself a maxi. 48 is greater than equal to its children. 15 is also, 59 is also, 11 is also. First node, which is non-heap, is this one. Effectively, if I have n nodes, the last node's parent is the n by 2 index. So this is the first node which might not be having maxi, might not be satisfied. From downwards. So n by 2 is one node, n by 2 minus 1 may be another, n by 2 minus 2 may be another, up to 1. These nodes are those nodes which might not be satisfied. And our purpose will be to make them satisfy. How to do? 61 is here, which I will check with its children. 19, 61, okay. Current node is okay. I am talking this as a root. So downwards only, upwards I will not check. Upward will be checked in the next iteration by some other treated as a root. Now consider 1 as a root. Once 1 is a root, out of these, root should be greater than or equal to both children. Equality, I'm not taking, say all unique values. So effectively means out of this, 48 should have been the root and 1 should not be. So 15 will be undisturbed. This will become 48 and this will be changed to 1. So these two values will be swapped. Now 48 satisfies. 1 is already leaf, so 1 may not go further down, but otherwise we have to check. 17, 11 versus 59. Yeah, 17 is already okay. Nothing to be changed. 5. So we are going like this, reverse order. I started like this and then going like this and again I will go like this. 17 satisfying. Now I am coming to 5. 48 versus 61. 5 has to be changed. It will become 61. This will become 5. But I'll not stop at 5 now because 5 now might be violating the downside. So again 5 will be compared with its children. That will further mean this becoming 19 here and this becoming 5 here. 5 is now leaf, nothing else to be done. 61 reaches here. Next time. Now, effectively, what I have got is a 26, 61, 77. At present, I have 48. At present, I have 19. Here I have 15. Here I have 1. Here I have 5. 17 has 11, 59. So now, root is to be checked. 26, 61 versus 77. This will mean this will be swapped. This becomes 26. But I don't stop here because this will be further checked. 15 versus 26 versus 11 and 59. This has to be further changed. This becomes 59. This becomes 26. So now this is a max heap ready. And you can see highest value is already on the root. So internally, storage is actually as an array. So in the initial array, the value was 26, 15, no, sorry, 05, 77. Then I had, after this 11, then I had, sorry, this was 1, 61. Then I had 11, then I had 15, then I had 59, 15, 48, and 90. This was your initial array. After adjustment of all nodes from index n by 2 up to 1, the array will become like this. Now the array will be this one. This one means 77 on the top. Then 6. This is node number 1. This is node number 2. This is node number 3, and so and so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Level order traversal. So effectively 77, 61, 51, 59, 48, 19, 11, 26, 15, 1, 5. This is index 1. This is index 10. And it is actually max heap now. So whatever on tree this side we saw actually happened here. This is node number 1 initially, and this was node number 2, 3, 4, 5. So from node number 5 was the first point we started. We said from this point 61 to be compared with its children. So I'll say, where is 51's left child? At index 10. I will compare 61 with 19. Everything being done over an array, visualized this way. So I'm thinking happening like this, but actually everything happening over array. 61 was compared with 19 and effectively no change. Then 1 was compared with its left and right child. 1's left and right child were here, 15 and 48. This meant this was changed to become 48 and this became 1. Then this was compared with its both children. 77 was compared with 11 and 15. Okay. 5 was compared with its both children. 5's children are at node number 4 and 5. So 5's children were 48 and 61. And we found that 61 reached here, 5 came here. Then 5 was further compared with its children. And when 5 was compared with children, I found a 19 here to come at this place, and this became 19 and this became 5. So this is how internally everything happening over an array. Every exchange swap happening on an array. In array. Everything will be over an array. Left child will be at index 2i. So I will compare with the 2i value. Right child will be at index 2i plus 1. So I will be able to reach there, compare with these two, and swap, etc. being done. So everything is done over an array. This will be ready. Once this sorted list, once this is unsorted, but maximum is here. So my next step will be, I will bring 5 here, take 77 at the last, and now I say, forget about 77. This is your new list, shortened list. Again, max heap this. Ultimately, out of max heaping this, 59 will come or 61 will come on the root guaranteedly. Next time, 61 will be taken at the last, and so and so. So effectively, next time my list will be considered as 5, 61, 59, 48, 19, 11, 26, and 50, n equal to 9. Now this list to be again heapified. Out of this, only your index 1 might not satisfy the property. Rest are already satisfied. So I will effectively adjust for index 1. Means on index 1, I will apply the same property. 5 index 1 will mean 1 being compared with its children. Its children are 61 and 59 at index 2 and 3. 2 and 3 out of this index 2, that left child is bigger. So effectively here it will come 61. It will come here 5. But I will not stop. 5 will be compared with its 2 children further. 5's 2 children are at index 4 and 5 because it is at index 2. So 4 and 5 out of this 48. So 5 will be again replaced and 48 will come here. 5 will come here. 5 will be further compared with its 2 children. Out of this 26 will come here and 5 will go here. So that will again do all exchanges, and now I find ultimately 61 will reach. Same process will repeat. 61 will be brought to the last, and then last 15 will come here. You will have a 61 here. You will have 15 here, and now forget about the list. Consider remaining list and repeat the process. So this is how heap sort works. Of course, relatively not that easy to understand initially, but with practice and once we will repeat, it will be more clear. So I repeat now, say initially I had some CBT available, might not be the full max heap. So I say from non-leaf nodes I started, backward up to root. So up to root means up to index 1, and non-leaf effectively means n by 2. If n is odd, it will mean still a floor of that, and up to this. For each of them considered as a root, you will do the adjust operation. So adjust oblique heapify. Once done, full max heap ready. Then highest element to go to the last and reduce, or to be, let's say, swapped with the last element and reduce the list size. And then you keep on looping. And finally, once list has only one element, things will be over. So this is going to be my overall heap sort. Now, out of this, it has mainly two main issues. First, we will have to do it for many nodes, heapify. So reduce the last size and adjust for the root. Root has violated the property. So for the root, it will be again adjust and again process. So this process we will see as one part. So effectively, I say I have step one, where for some nodes, let's say for I equal to n by 2 backwards up to 1, I have to adjust. Many nodes are non-leaves to be adjusted. All non-leaves. So all non-leaves to be adjusted or heapify. That is first step. After that, step 2, main step will be your max heap based extraction and highest element, etc., etc. Highest element swapping and adjustment. And this process to be repeated. So 2 steps. So let's go one by one. Step 1 we will talk today. Step 2 we will talk next time. Step 1. First of all, what I have to do. So let's start making, first of all, a void heap sort. So my heap sort is to be implemented. For heap sort, what parameters I require? Obviously, I require one array and the corresponding size with proper syntax. If any I'm missing, you can add that. And assuming that array has elements at index 1 onwards, not 0 to n minus 1 now, we are assuming indexes to be 1 to n. So now, in this what I say, for non-leaves, I have to apply adjust operation. And for how many non-leaves are there? N by 2 backwards up to 1. So I'll say this for I equal to this, I have to do. What I have to do? I have to call adjust or heapify function. What parameters I need, I will decide. And this process I will do. And now max heap will be ready. Once max heap is ready, then my step 2 will come. So step 2 code we will write here later. Step 1 code effectively we are partially ready. Adjust function we will write as a separate function because that will be needed in the step 2 also. But for step 1, I am calling it many times for all non-leaves. In step 2, that step will be called only for a root. So adjust or heapify function to be written. Void adjust or heapify, whatever you say. The function name, I am writing both so that you remember that you can use anything. What parameters it needs? Of course, it will need your array. Without doubt anything. What else I need? Which index onwards I am starting? First time I want to start with this I as 5 for list was 10. So from 5 node downwards I want to adjust. Next time I will become 4. So I will say initially I have to do from 5 node downwards, then from 4 node 4 downwards, then for 3 downwards, 2 downwards. Means my current route from where downwards I will go, upwards I will not. So I will need some index. Let me name it as index with proper syntax, whatever you write. but index will be supplied, which will be considered as a root. And root effectively means its children are satisfying the property, but root might not be. So children are already max heap, but root might not be. So its children are leaf always initially, and they are guaranteedly satisfying. So from which index I start, I will be using this property. What else I need? Maybe I need nothing. I could progress further. If I need, I will add some parameter. So what I have to do? I'm given index. I have to refer to its left and right children and compare with them. Where is its left children? Left children is going to be at index into 2. So 2 star index. Where is going to be its right child? Right child index will be at 2 star index plus 1. Now what? Effectively, I have to check, is root or is array root, array index highest, greater than equal to its children value or not? That step you have to write. If yes, work is done. Otherwise, I have to do swapping. So I want you now to try to write the code for this. If not, swapping. If yes, effectively over. So you should think what to do and how to do this. I'm giving you a pause. Try this, and once you are ready, we will come back to this place. And then, of course, some repetition, looping, etc. may be needed if needed. That we will define later. But primarily, this is going to be the overall structure. So I'm giving a pause, try for something, and then I'll come back here. Those who want to try, they can give the video pause and then try. Once you resume, I will be discussing the solution in more detail. So parameters, of course, your array is with syntax written, index written, and if I need something more, I will see. I have found left equal to 2 star index. I have found right 2 star index plus 1. Is it guaranteed that right child exists? Might not be. Left child exists because we are calling heapify or adjust only when we are starting with some parent. But parent has both children, might not be. For example, in our case, when I was 5, we were on the first parent, then it has a left child at index 10, but index 11 didn't exist. How we will come? If the right is less than equal to n, only then right child exists, otherwise not. So I will need n also to be passed here to confirm that whether child exists or not. If child doesn't exist, we will not compare with the right child at all. Now what I have to do? Out of current root, I have to find whether it is already highest. If not, I have to swap. So I will do what? I will assume my max index to be, let's say, currently index, given index. So I'm assuming root is the highest. Root's value is highest. If it is not, is higher than its children. If it is not, we will swap. So max index currently, I assumed this. Now I will compare with the left child and find if left child is greater, obviously max index has to change. How to do that? Compare the value with the left child's value. Which value to be compared? ARR max index or index, whatever you say. Currently root being compared. If this value is less than the left value means ARR left. Left is index of the left child, and left child guaranteedly exists. So I say if left child is greater than this, then obviously max index has to change. Max index should become left, but left might not be the highest. Right child could be even higher. So I must check that. How to do that? So I will say, again, I have to check array right to be compared with the max index value, not just max index. Remember, you have to write array max index, not only max index, because values are to be compared. If this value is greater, obviously max index will be right side, not just the previous max index. But I have left some space here. Obviously, I'm sure some of you are able to guess. Right child might not exist at all. So before comparing, I must check whether right child exists. Right child exists or not, I can check it by saying right less than equal to n, and only then I will do this comparison. If right is already out of the range, then out of left and current root only, I have to find the highest. So once we come out of this, now my max index is guaranteed to have the highest value. If current root itself is the higher out of this, I have no further checking to be done. So effectively, I can say I need not unnecessarily waste my step or keep on iterating, because current value itself is okay. No further downwards to be done, no swap to be done, no further adjustment needed. How to verify whether the swap will happen or not, whether my highest value is on the root itself or not? That I will verify that if my max index is equal to the roots index itself, and roots index was effectively index. So if it is so, effectively I can say no exchange is happening. All things are okay. I can break or return. Because, okay, now things are okay. Maybe in first iteration, maybe after subsequent iterations, some. If I have a big CBT of 120 to 200 elements, at some point I find that root is satisfying the property and higher than the children. Children are already satisfying property, so no further need to go further. Else, if it is no, then what to do? I have to swap. Swap whom? The value at the max index versus value at the index, or value at the parent. So parent is at max index by 2, or index also, whatever you say. So effectively array max index versus, I'll say versus array index. These values are to be swapped, where it is guaranteed that index is always equal to max index by 2. Guaranteed, because I'm swapping, that means it is being swapped with the parent, and obviously it will be always this. But even if I have done already, so I need not bother swap this. But after swap, for example, I have got 1 here, I had here 11, I have got 59. Let's say 59 comes here, 11, 1 reaches here. Earlier 59 was greater than this side's values, 48 and 19 maybe. But now if 1 reaches here, 1 is further to be adjusted downwards. That means from here again, consider index to have changed to max index. Earlier, my index, let's say this was index, let's say 2. So obviously this was a 3 and 4, and these could have been certain values at index 8 and 9, obviously. So if a 2 has been swapped with the index 4, my next iteration should continue from index treated as a 4. Earlier index was a 2. Now index shifts to the max index direction. So this becomes index. Again, this should be compared because value 1 reaches here. So 1 should be compared with 59 has gone, 1 has come here. 1 must be compared with 48 as well as 19. So maybe 1 will have here. This will mean 1 reaches here. 48 will come here. This might have further children at 16 and 17 index. So there could be some value, let's say 20, maybe 44 at index 8 and 9. Again, I have to continue like that because this is your index 8. So 8 will mean this index will be 16. 17 will be the right child for 8. Again, proceeds like this. So that means consider this max as this and repeat back. So effectively, I have to loop back. Loop for now, what should be the condition? So that means I have to repeat for certain times. So this will be a while loop. Till what time I should continue, as long as I don't go out of reach. So if my index has some child, at least one child, only then there is worth to continue. If index is root, if index is leaf, effectively stop. Whether index has some child or not, that is guaranteed that if index is less than or equal to n by 2, it has some children, otherwise not. If index is n by 2 plus 1 onwards, they are guaranteedly leaf. So effectively, I can have a condition here, while index less than equal to n by 2, you can have a loop here and you can continue to have your loop repeated. So more or less, my adjust function is ready. I will say you to revise and review this. And you should be able to understand this, that you are able to make max heap by calling initially n by 2 down to 1 as index. So makes the initial array as max heap. Calling this adjust function these many times. So I think with this I will stop, and I'll suggest you to revise concept of a CBT. Then why CBT? The purpose was over array we can work and use the children also, use left child, oblique right child, oblique parent. Directly index will be ready. Using this, I have used CBT. So then I have to understand to do this as adjust or heapify to make it max heap. And for making it max heap, multiple times heapify function is being called for the first time. Because except root, except leaf, all other nodes were not satisfying max heapify property. So subsequently, once max heap is ready, my heap sort will work. Revise this, try to code it for adjust at least. Whatever we have discussed, step 1 must be coded, and then step 2 we will discuss next class. So bye-bye, all the best to all of you. Have a good day. Practice your binary search tree also. So, or practice, or I'll say code step 1 of heap sort, including adjust. So this is my homework. And also code, revise your binary search tree, because that also we will need in the next class. Insertion and search, these two operations we have already done. So revise this also. If you have not coded till now, do that coding also. This is your homework for today. Do this, complete this. Next class, we will have these concepts utilized. Bye-bye. All the best to all of you.